I saw two different kinds of answers in your responses, both of which are interesting and show an understanding of the underlying problem. But you seem to be answering two slightly different questions. So I guess the first thing I would say is that this question was specifically asking, how do we construct C such that we can just repeat the cycle over again on the new distance matrix that we're going to get by replacing xy with C. So that really comes down to the Ultrametric assumption, namely that since distance is just proportional to time, therefore that for a set of modern sequences, we can immediately identify a neighbor pair by the pair with minimum distance. That really depended upon this assumption that we talked about a few minutes ago, that all of the sequences are contemporaneous. In other words, that they're all at the same time point. So if we violate that assumption, I think you can see that the Ultrametric assumption could actually pick a wrong tree. So let's see. Say we had an example like this, where we've got a pair of sequences, let's say Z, W, and let's say we had the following situation. X, Y. So this is drawn to indicate that these are all at the same time point, modern sequences. One of the things that I saw people suggesting was basically to compute the distance from this internal node basically to the other sequences ZW. So that would be like labeling that internal node directly as C. Okay? I think you can see the problem with that, which is that the distance from here going through to W, say, is less than the distance from Z going to W, because we've placed this basically very close to this internal node, much closer than it is to either the sequences Z or W. So if we place C here, we would erroneously pick C as a neighbor of Z or W, whereas Z and W are actually neighbors. Okay? So, long story short, the condition that we require for being able to fit the assumptions of the Ultrametric phylogeny algorithm is we basically have to place C contemporaneous with X and Y. So that would instead be like placing C, down here instead. Okay? So how would we place C down there? Well, maybe we should emphasize that, of course, even though we expect equal distances, for example, from X or Y to any of these other sequences Z or W, there's still a stochastic mutation process occurring here, right? So it can have random noise in it, right? So we might get that the distance from X to Z is not exactly equal to this distance from Y to Z computed from our actual observed data. So if we want to get the best possible estimator for the distance for C from Z and W, by the law of large numbers, the best estimator we can get is basically to just take the average. So one simple way of saying it is that the distances that will compute from C to Z or W or any other sequence other than X or Y would basically just be the average of their distances from X and Y. Okay? So the first point being that this is a way of constructing C such that it is contemporaneous with X and Y, and therefore contemporaneous with Z and W, and therefore valid to apply the assumptions of the ultrametric phylogeny algorithm for one more cycle. Okay? So it's basically like we're applying the same algorithm onto data that fits the same assumptions that the first cycle assumed. Okay? Question? So under this picture, I think you'll agree that delta CZ is less than delta ZW. Do you agree with that? Whereas in this picture, Z and W are neighbors, not C and Z or C and W. So this would be a clear example of a violation of our original assumption that we could pick neighbors by minimum distance. And the thing that prevents, that makes the minimum distance assumption valid is that we're assuming that all of these leaf sequences are contemporaneous. Therefore, the distance between them is just the time back to their most recent common ancestor.
Would it be equivalent to essentially update all the distances by, I guess, subtracting the distance from X to the parent node C, the most recent common ancestor? Or like, so that segment that you have.
Sorry, subtract from what set of distances are we going to do this subtraction?
So we have our entire list of pairwise sequences between every pairwise distance between every two sequences or whatever. So would it be equivalent to go through that list and subtract the distance of that segment you have right there from C to C? So kind of like rolling back in time to the previous most recent common ancestor.
Doesn't sound right, because we have other branches in here that are not necessarily, yeah, no, it doesn't sound right. So I can draw examples like, I mean, here I place C fairly high up in the picture, but you could imagine cases where, let's say that's the closest pair that we're going to replace, and we might have, you know, additional pairs in here, right? So the fact that we're cutting off that amount of distance here doesn't mean we should go cutting that off over here as well, right? Because we're going to have to sort out who to join over here based upon their pairwise distances, and their pairwise distances aren't affected by, it's only the distances to X and Y that have this extra distance in them, right?
I mean, if you just, does my question make sense?
Well, so let's look at the whole picture of what we're trying to do. So not only are we trying to get the ordering of the branches, we're also trying to actually compute the distances. So on each edge, okay. So the general idea of, you know, computing where the location of this internal node is based upon basically subtracting out half of the distance between X and Y to connect back to the other sequences. That part is valid in that it gives you information about the location of this internal node relative to the other sequences. But basically throughout this whole process, every time we join a pair, we're going to write down a distance on that edge. So we don't really want to go artificially like doing funny things to the other distances. You might be able to get the right ordering out, but for the purpose of being able to extract accurate edge lengths and branching order, it's convenient basically to replace X and Y by a new sequence that's basically contemporaneous with them. Other questions?
Is the distance from X and C the same as the distance from Y and C?
So you're talking about this internal node here. Yeah, under the ultrametric assumption it is.
Okay. So you take the average, I guess, from the new between IC, which is temporary to C.
You're talking about the one down here.
Right.
Yeah.
Will it just be like on Y or on X?
Well, again, there's noise in the real data. So the expected distance is equal, but the actual distance from any place to either X or Y could differ basically just as you could think of it as sampling noise, sampling error, because on any given path, mutations occur randomly, stochastically with a fixed set probability. But the actual distances for a set of sequences are computed from the observed sequences, which is noisy. Okay.